give a talk sort of following up on what Dan was discussing. So there's been, in my opinion, there's been a lot of really good work on how supermassive black hole seeds could have formed. And there's been a lot of work on how they can grow to be very massive once you have a large enough seed. But really understanding how the actual seed formation pathway can affect populations of black holes across all cosmic time, across different mass ranges. It's a very difficult problem, but I don't think there's been enough done with it. So that's what I've been looking at for a fair while now. So I'll talk about this project I've been doing. It's all post-processing simulation. So I'll give a brief simulation overview and then move pretty quickly into how we can post-process that and change how seeds form and what we can learn from that. So it's a cosmological simulation that I work with. So you have a huge volume, but then you have physics going all the way down to smaller scales. Specifically, for this project, I've currently been using Illustris. We've had a number of Illustris talks, especially if you include TNG, which is similar physics anyway. So I'm not going to try and reiterate all of the physics involved in Illustris, but if anybody wants to talk about that afterwards, I'll be happy to. What's particularly significant for what I'm doing is how you model the black holes. So there are, broadly speaking, three aspects to a black hole model within a simulation. So the first thing is, how do you form it? And so Illustris takes a very simple model, which is the one that I think is most commonly used in cosmological simulations, where you don't try and model the formation at all. You just say, well, if you get a large enough halo, we expect there should have been a black hole that formed at some point in the past, so we'll put one in now. So if you get a halo above 5 times 10 to the 10 solar masses, if there's not already a black hole, put in a black hole of 10 to the 5 solar masses. Once you've formed the black hole, or in the case of a simulation, just put one in, you then have to have it grow. So there are two ways of growing. You can have black holes merge with each other, which all simulations do, and then you have gas accretion. So Illustris uses, again, one of the more common approaches, which is a Bondi-like formalism for the accretion rate. So we allow the black hole to grow, which depends on gas properties, specifically the density and the sound speed. And while they're growing, you have black hole feedback. So we've discussed feedback a fair bit, supernova feedback more so than black hole feedback, but it's, again, using subgrid models. Illustris puts in quasar mode feedback when you have efficient accretion, and that's an isotropic thermal deposition of energy. And you also have radio mode where you're depositing energy in offset bubbles. And there's a radiative feedback by modifying the photoionization and photoheating rates. So we have a nice overall view of how to model black hole growth over cosmic time in this simulation. So Illustris has been used to match a lot of things. We heard about TNG as well. Here's the quasar luminosity function. So at low redshift, it matches very well. At high redshift, the bright end does pretty well. The faint end, you have significantly too many compared to current observations. But there's some questions about how realistic the initial seeds are, which is what I'll be getting at. You've also got scaling relations, which are found to work very well. It's somewhat tuned to match the redshift 0 scaling relation, but it also matches at higher redshift, which is always nice to find. What I'm particularly interested in is how you actually form these seeds and what that can tell us. So as Dan discussed, there are several commonly used pathways. So you have direct gas collapse from a massive gas cloud that collapses directly into a black hole or possibly into a supermassive star, which then will collapse to a black hole. And that will give you seeds potentially on the order of 10 to the 5 solar masses. And at the other end, you have POP3 stellar remnants, which are much lower mass initially, and as Dan was discussing, might have some difficulties growing to be the earliest supermassive black holes. But this gives us a very wide dynamic range. You're talking 4 orders of magnitude in what this initial seed mass could be. And it's all occurring in a whole range of different metallicities. Because depending on the metallicity of the gas, it'll fragment differently, which can produce very different masses. But so what I wanted to know is, can we use these different seed models and see what those will do to the overall population? And so I do that with post-processing analysis. So the idea is, I want to change this. So instead of just putting these black holes in when a halo gets large enough. I'm going to do something more physically motivated. But rerunning the simulation is expensive. It'll take tens of millions of CPU hours. And when you want to do a whole lot of tests on different types of seeding, that's computationally problematic. But what we can do is just recompute the growth. So instead of rerunning the simulation, we take all the output from the simulation and take advantage of the fact that the local gas properties to the black hole are saved at every time they're calculated. So we can actually recompute the entire growth history if it had been seeded differently, without having to rerun the whole simulation. Now, the one downside to this is feedback is then unchanged. Because we're not rerunning the simulation, the feedback was already put in, we can't change that. So we're limited once we start getting to the most massive black holes where feedback is important. But until then, this lets us recompute the whole history and do a pretty good job with, you can run it on a desktop in an order of a day instead of tens of millions of hours on a supercomputer. So here's an example. This is the most massive black hole in Illustris. In red is the most massive progenitor, and in black are all of the other black holes that it merged with. So at redshift 0.5, this is just one black hole, but this shows you the full history at earlier times. And this is what happens when I recalculate it using a post-processing method. So it matches, which is a good check, but also doesn't really give us anything scientifically interesting. But we don't have to just blindly recompute it. So here's an example. This is, again, the one I just showed you. But now I've changed every single seed mass. So instead of being seeded at 10 to the 5, I give it a Gaussian distribution around 10 to the 4 solar masses when they're seeded. And so you end up with these black curves. The red line is the most massive progenitor from the original Illustris simulation, and in black are with the new seed masses. So you can see we end up about an order of magnitude less massive, and at higher redshifts you have a much wider range of black hole masses. So we are able to see how these things change quite significantly. Now what I'm doing for the rest of what I'll talk about today is not changing the mass of the seed, but instead where and when we seed them. So I did a number of tests on different seed possibilities. So one is I just seeded only a randomly selected subset of what Illustris originally had. I also tried seeding where I seeded it based on instantaneous properties of the galaxy when Illustris seeded it. So we looked at putting some cut on the local gas spin, for example, or a cut on the local gas metallicity. But then the most interesting one is where we do a model which is based on a physically motivated model for direct collapse. So we say we're only going to seed it if it's a massive enough galaxy. It has to have very low gas metallicity so that it won't fragment. And it has to have a sufficiently low spin so that it won't be rotationally supported. And we do this, we look at every single progenitor galaxy. So here's a redshift 5 black hole that was seeded in Illustris. And this is all of the progenitor galaxies involved in that. And we find that this point is when a direct collapse black hole should have formed. And so I would seed this one and regrow it. And here's another example. So a lot of these progenitor trees get much more complicated. There's a lot more to look at. But we do this for every galaxy in the simulation. And we allow for a more physically motivated seed model. And so then we get something more along the lines here. So you've got your original run. If you only seed 10% of those, you get something that looks like that. If you seed only 10% of them, but where you're selecting it based on local gas properties, you get something slightly different. And then here's when you do our direct collapse model. So in all cases, we end up with a final mass that's within an order of magnitude. But you do have a significant variation there, and more significantly, high redshift, low masses, you have a very wide distribution. So changing our seed model can give us very big differences. This is in one individual black hole, but we do that for all of the black holes in the simulation. And so now we can see the luminosity function at redshifts 4 and 2. So you can see, as you might expect, if you seed more rarely, you have fewer luminous quasars. And so we end up with a nice distinction in the bright end and all the way down to the faint end of the luminosity function. And unfortunately, it's sort of consistent with observations because high redshift luminosity function observations are very difficult. We then continue that down to low redshift. And for instance, at redshift 0.5, you can see the luminosity function converges. It's no longer sensitive to the seed model. So if you can push the faint end luminosity function, that will let us differentiate between these models, but the bright end doesn't help. You do the same thing with a mass function, and it's qualitatively similar, except at low redshift, it's not converged. So if you compare just at redshift 0.5, here's the luminosity function where all the models have converged nicely, but the mass function, they are still different. So this is telling us that in the models which have seeds form more rarely, the most massive black holes are actually slightly less massive, but they're still equally luminous. So they're growing more efficiently. So that's actually giving us a potential way of differentiating between these models. So we can explicitly look at that. If we plot the Eddington ratio distribution function at redshift 0.5, you can see going from black to blue to green to pink, we're getting to progressively more constraining seed models. And you can see that pushes the distribution to be more efficient accretion. So at low redshift, just the Eddington ratio distribution function gives us the potential to differentiate between these. But if you just go up to redshift 1, they all pretty much agree. And at higher redshifts, they agree even more closely than that. So it's only low redshift where we can use that to tell the difference. But where you get the best potential for differentiating between models is where you might expect, which is the merger rates. So obviously, if you seed black holes more rarely, you have fewer black holes in the universe. They're not going to merge as frequently. So here I've plotted, this is the number of mergers, the cumulative number of mergers above a given redshift for a variety of chirp masses. So chirp mass is what gravitational waves are detecting, which we aren't getting for supermassive black hole mergers yet, but from LISA we should be, and there's potential from pulsar timing arrays as well. So if you look at this, in the original simulation, here's the cumulative merger number for all and going to progressively higher mass mergers. So you can see, pretty much it doesn't matter. Any given mass threshold you use just changes the normalization, how frequently we see these mergers. If we seed more rarely, but just a random subset, it has no significant impact on the shape of this. It just changes the frequency you see it with. But if you go to the direct collapse model, they're actually being seeded in a more physically motivated way, and they're tending to be just seeded high redshift. And so you actually end up changing the shape. So at the low mass mergers, you're tending to find they tend to happen much more dominantly at high redshift. Once you get down to low redshift, you're starting to get the more high mass mergers. So by checking the redshift distribution of observed mergers, you can tell the difference between these models. But it gets even more strong than that if instead of looking at just the chirp mass, which is a combination of the two masses involved in the merger, if you look at the individual masses. So here we're plotting, on the x-axis is M1, which is just the mass of the more massive black hole involved in a merger, and the y-axis is the less massive mass. So in the original simulation, this is the distribution of mergers that happen over all time. And you can see it peaks around merging black holes of about 10 to the 6.5 and 10 to the 6. That's where we get most of the mergers. But you also have an awful lot involving a very high mass black hole and a very low mass black hole. And if you seed a subset, just seed half of that or a tenth of that, it's a very similar distribution. It's not exactly the same because of the way mergers work, and I've quantified the difference that I won't get into here, but it's qualitatively very similar. But then if you compare that to the direct collapse model, it's suddenly very different. So what's happening is, in this model, all the seeding is happening at high redshift. So at low redshift, you don't have any low mass black holes left, or you have very few. So it's incredibly difficult to get a very massive black hole merging with a low mass black hole. So if you can quantify the distribution of merging masses, this is a very good way of differentiating between how supermassive black hole seeds could have formed. And potentially counterintuitively, the lower redshift the mergers are, the easier it is to differentiate. Because at high redshift, you're tending to mostly get in this range, because none of the black holes tended not to have grown very much, and the ones that have don't undergo too many mergers. But once you get to low redshift, that's when you start getting a lot more of these, because you have those very massive black holes that can merge with others. And at that point, if you look at the distribution of low redshift mergers, that's actually the strongest way to differentiate between how the original seeds would have formed, which we're mostly talking about redshifts 7 or 8 in the simulation. So, to conclude, there's a lot of the black hole population which is not strongly impacted by changing a seed model. The highest mass black holes tend not to be significantly changed, so they are affected a bit. But if you're interested in looking at relatively low mass black holes or at relatively high redshift, it's actually very important to incorporate a very accurate seed model. And just using the typically used model where you say, we're not going to worry about the initial bit, we'll just put one into every halo, you're really starting to lose a lot of information there. So in particular, I want to emphasize the efficiency with which they grow is pretty dependent on how the seeds initially form, and also the merger rates. So there's a lot to look at there. There's a lot more in this analysis I haven't discussed, where we looked at the initial growth and how you can actually have lower mass seeds that can grow at sub-Eddington rates but still be consistent with cosmological simulations. And then we have additional areas where we're adding additional constraints for direct collapse models. We're adding seeding using from POP3 stars and from interactions in dense nuclear star clusters. And then zoom-in simulations that incorporate these models in sort of artificially and self-consistently in comparing how everything works with one another. There's a lot still to look at, but I think it's pretty clear that it is important to consider how they seed, even if what you're interested in are the more massive or low redshift black holes. It does make a pretty big difference. Thank you.
Thank you very much, Colin. I'm sure you have plenty of questions.
I can just yell. Hi, Colin.
Hey.
One thing I was a little confused about is a lot of the conclusions that you kind of went through seem to either directly or indirectly focus on the massive black holes at low redshift. But aren't those the ones where you told us at the beginning of the talk that we should be careful about because they will be affected by feedback?
Yes. So this starts getting into a lot of details that are too much to talk about in a short talk. So, like I said, lots of other things that I have. So if you look at the scaling relation, the top panel here is the colored pixels in the top panels are the original simulation, and the contours are the regrown black holes. And the lower panel is the same as the contours, just shown differently. So what you can see is at high redshift, it matches perfectly, and that's because you haven't gotten into the self-regulated regime, so you don't have to worry about that issue. Once you get down to lower redshifts, this, where it comes down a bit, that's where we're saying we're less well constrained. It's possible that this is coming from too much feedback that is because the black holes are too large. So much of this, we've actually done a fit to the original and a fit here, and then we adjust the most massive black holes upwards according to the difference in slopes of these scaling relations. And it does make a difference, but the qualitative aspect of the conclusions remain quite strong. And shifting this all the way up is very conservative. Obviously, it should actually be less massive because they started out less massive. So the end conclusions, I think, are somewhat robust to that as long as you're not worried about the exact magnitude of the difference.
So maybe you already talked about this, but what about your direct collapse black hole model sort of excludes dwarf galaxies from having black holes, or is it just that you don't have many dwarf galaxies in the simulation?
It's basically because we can't have it if the original simulation didn't have a black hole.
Okay.
So because of the way it works, I'm recalculating the growth based on the local gas data around the black hole from the original simulation. Now, having said that, it's important to consider all of those other ones. So I didn't put any of this into the talk, but I've also done one where I only look at seed conditions, and then instead of growing according to the properties from the simulation, I try different analytic models for growth and use that to try and constrain it. And we actually find that most models that are very simple are not going to match. It either messes up the high redshift or low redshift, high or low end of the mass and luminosity functions. So there is one model that works, which is dependent on how overmassive a black hole is compared to its host galaxy. And that naturally gives you excellent agreement with observation.
Does that also affect your merger rates? Like, I mean, because you don't have very high mass ratio mergers because you don't have any black holes in small galaxies, presumably.
So that is something I'm still looking at. The analytic model is a lot trickier to determine when mergers should happen because I don't have original black holes to tell me when they merge. So it actually requires looking at all of the galaxy merger trees and estimating that, and that has not been finished yet.
So we have a last question while the last speaker is preparing his or her computer, please.
Hey, Colin, have you thought about calculating the various gravitational wave backgrounds that would come out of these different seeding scenarios? Because with direct collapse black holes, especially multiple objects, you could have...
Yes. So, since he's setting up, I won't try and go back inside. So looking at the chert mass rates, we're taking those kind of plots and doing a more involved analysis. So we're making estimates on detection rates for LISA, not for pulsar timing arrays specifically, but general merger rates, so we can estimate the detectability rate of these mergers, and then looking at a background will be a next step after that. But yes, it's something we can certainly do, and we're planning to.
Let's thank Colin